Well, let me tell you something that should bother you. Right now, as you sit there, you are made of atoms, trillions upon trillions of them. And every single one of those atoms has electrons surrounding a nucleus. You know that. You probably learned it in school. But here is what they probably did not tell you. According to every equation physicists had in the early 1900s, every one of those atoms should have collapsed in less than a trillionth of a second. Not a billion years from now, not slowly, over time, instantly. The math was airtight. An electron moving around a nucleus is accelerating. And accelerating charges radiate energy. That was not controversial. That was not a guess. That was James Clerk Maxwell's equations, the most successful equations in all of physics at the time. And those equations said, with absolute certainty, that the electron should lose energy, spiral inward, and crash into the nucleus. Every atom in the universe should have self-destructed almost the moment it formed. And for 14 years, not a single physicist on Earth could explain why that did not happen. 14 years of the smartest people alive staring at this problem, and nobody had an answer. Think about that. Now I want to take you through this story because I think it is one of the most beautiful stories in all of physics. It is the story of how we discovered that reality is not what it looks like. And it starts with a very specific number. You see, there is a formula in classical physics called the Larmor formula. It tells you exactly how much energy an accelerating charged particle radiates away, and you can use it to calculate precisely how long a hydrogen electron would survive if classical physics were the whole story. So let me walk you through this. The electron in a hydrogen atom sits at what we call the Bohr radius, about 0.529 angstroms from the nucleus. At that distance, the electron is experiencing a centripetal acceleration of approximately 9 times 10 to the 22nd meters per second squared. That is an absolutely enormous acceleration. Now, you plug that into the Larmor formula, and you get a radiated power of roughly 46 nanowatts, 4.6 times 10 to the minus 8 watts. That sounds like almost nothing, right? 46 nanowatts. You cannot even feel 46 nanowatts. But here is the thing. The total energy of that electron in its ground state is only negative 13.6 electron volts. That is 2.1, 8 times 10 to the minus 18 joules. A breathtakingly tiny amount of energy. And at 46 nanowatts of radiation loss, the electron dumps every last bit of its orbital energy in approximately 16 picoseconds. That is 1.6 times 10 to the minus 11 seconds. 16 trillionths of a second. Not 16 seconds, not 16 milliseconds. 16 picoseconds. The atom does not even get to exist for a single nanosecond. It is gone before it begins. And this is not some edge case. This is not a weird exception. This is the prediction for every hydrogen atom in the universe, every atom with an electron and a nucleus. According to classical electrodynamics, matter itself is impossible. Now, let me tell you how this crisis actually unfolded because the human story here is remarkable. In 1911, a physicist named Ernest Rutherford did one of the most important experiments in the history of science. He fired alpha particles at a thin gold foil, and most of them passed straight through, but a tiny fraction bounced back at wild angles. Rutherford himself said it was as if you fired a cannon shell at tissue paper and it came back and hit you. What he discovered was that atoms have a tiny, dense, positively charged nucleus at the center with electrons somewhere outside it. This was the Rutherford model, and it was a triumph. He had figured out the basic structure of the atom. But there was a problem, a devastating problem. You see, Maxwell's equations were not optional. They were the foundation of electrodynamics. They describe light, radio waves, magnetism, electricity. They work brilliantly. And Maxwell's equations said, without any ambiguity, that an accelerating charge must radiate electromagnetic energy. An electron moving in a circle around a nucleus is constantly changing direction, which means it is constantly accelerating. So it must radiate. And if it radiates, it loses energy. And if it loses energy, it spirals inward. And if it spirals inward, it hits the nucleus. in 16 picoseconds. Sir Rutherford had proven what atoms look like, and Maxwell had proven that what atoms look like cannot exist. Both were right. And yet here we are, made of atoms. This was a genuine crisis, not a minor puzzle, not a footnote. This was the most successful theory in physics telling you that you should not exist. Every chair, every star, every molecule of water, every strand of your DNA, all of it should have collapsed before it ever formed. And for 2 years after Rutherford's discovery, nobody had any idea what to do about it. Now, in 1913, a young Danish physicist named Niels Bohr did something very bold. Some people would say desperate. Bohr proposed that electrons can only exist in certain specific orbits around the nucleus, not any orbit. Only orbits where the angular momentum is an integer, multiple of h divided by 2 pi, where h is Planck's constant. And in these special orbits, Bohr simply declared, the electron does not radiate. Now you see, this is very interesting because Bohr did not explain why the electron does not radiate. He did not show what was wrong with Maxwell's equations. He did not provide a mechanism. He just said, in these orbits, it does not happen. That is it. He drew a line in the sand and said, the rules are different here. And you know what? Most physicists thought this was nonsense. And honestly, who could blame them? It is like saying, well, gravity pulls everything down, except on Tuesdays. Certain objects just float. No explanation. They just float. You would not accept that. And yet, Bohr's model worked, not a little, spectacularly. When Bohr calculated the wavelengths of light that hydrogen should emit, his predictions matched the experimental measurements with stunning precision. The Balmer series, those four visible spectral lines that physicists had measured for decades, 656.3 nanometers, 486.1, 434.0, 410.2 nanometers. Bohr's model predicted every one of them. His calculated Rydberg constant matched the experimental value to better than 0.03%. He predicted the ionization energy of hydrogen as 13.6 electron volts. An experiment confirmed it exactly. He predicted the Lyman series in the ultraviolet and the Paschen series in the infrared, and they matched too. This was not a coincidence. Something deep was going on. Rutherford himself, when he saw Bohr's results, was convinced, not because Bohr had explained why quantization happened, but because the numbers were too good. When your theory predicts spectral lines to within fractions of a nanometer, something real is being captured, even if you do not understand what it is yet. But here is where Bohr's model ran into trouble. It worked beautifully for hydrogen, one electron orbiting one proton, but the moment you tried to use it for helium, with two electrons, it failed. And lithium was worse. Anything beyond hydrogen, and the model fell apart. Bohr had found a clue, a tremendously important clue. But the real answer was still 12 years away. Now let me tell you what happened next, because this is where the story gets really beautiful. Between 1925 and 1926, two physicists independently cracked the problem wide open. Werner Heisenberg, working in Germany, developed a mathematical framework called matrix mechanics. And Erwin Schrödinger, working in Austria, developed a completely different framework based on wave equations. And here is something remarkable. These two approaches look nothing alike. Different mathematics, different philosophies, different starting assumptions. But they gave the same answers. Every prediction was identical. It turned out they were two different ways of describing the same underlying reality. And what that reality turned out to be was something nobody expected. You see, the question everyone had been asking was, why doesn't the electron radiate as it orbits the nucleus? And the answer, when it finally came, was not some clever fix to the orbit. The answer was that the question itself was wrong. The electron is not orbiting the nucleus. It is not a tiny ball circling a tiny core. It does not have a trajectory. It does not have a position and a speed at the same time. The electron is described by something called a wave function, a mathematical object whose squared amplitude gives you the probability of finding the electron at any given point in space. And for the ground state of hydrogen, that probability distribution is a spherically symmetric cloud, densest near the nucleus, fading exponentially outward. No orbit, no circle, no path at all. And this is the key. If the electron is not orbiting, it is not accelerating. And if it is not accelerating, it does not radiate. The problem is not solved in the usual sense. It is dissolved. The premise was wrong from the beginning. Think about that for a second. For 14 years, physicists were trying to figure out why the electron does not radiate while orbiting. And the answer is that the electron is not orbiting. It is a standing wave. And standing waves do not radiate. The atom is stable not because something prevents the collapse, but because the whole picture of a tiny ball spiraling inward was never correct. Now, you might ask, well, okay, so it is a wave, but why does the wave not just collapse into the nucleus? What keeps the electron cloud from shrinking down to zero size? And this is where we meet one of the deepest ideas in all of quantum mechanics. In 1927, Heisenberg formulated his uncertainty principle. It states that the product of the uncertainty in position times the uncertainty in momentum must be greater than or equal to h bar over 2. You cannot simultaneously know exactly where a particle is and exactly how fast it is moving. The more precisely you pin down one, the more uncertain the other becomes. Now, think about what this means for the electron. Imagine you try to squeeze the electron closer and closer to the nucleus. You are confining it to a smaller and smaller region of space. Its position uncertainty decreases, but the uncertainty principle demands that its momentum uncertainty must increase. And higher momentum uncertainty means higher kinetic energy. At some point, the kinetic energy cost of further confinement exceeds the energy you gain from being closer to the positively charged nucleus. The electron settles into a balance point, the ground state. The optimal compromise between wanting to be near the nucleus because of electrostatic attraction and needing to spread out because of the uncertainty principle. And here is something beautiful. That balance point, that optimal compromise, is exactly the Bohr radius, 0.529 angstroms. The size of the hydrogen atom is not arbitrary. It is not random. It is the precise point where quantum confinement energy and Coulomb attraction reach equilibrium. The atom has a definite size because the uncertainty principle demands it. The ground state energy is negative 13.6 electron volts, and there is no lower energy state available. The electron is already at the bottom. Any attempt to push it closer to the nucleus would require more energy than it would release. The ground state is the lowest eigenstate of the hydrogen Hamiltonian. It is not just the lowest energy the electron happens to occupy. It is the lowest energy that physics permits. You cannot fall below the floor. And quantum mechanics built the floor. Now, this opens up a whole question. If the uncertainty principle prevents one electron from collapsing into the nucleus, what happens when you have lots of electrons? What about bigger atoms with 10, 20, 50 electrons? Well, you see, there's another quantum rule at work here, and it is just as important. In 1925, Wolfgang Pauli proposed what we now call the exclusion principle. No two fermions, and electrons are fermions, can occupy the same quantum state. Each electron in an atom must have a unique combination of quantum numbers. And this has an extraordinary consequence. The first electron shell, the one closest to the nucleus, can hold only 2 electrons. The second shell holds 8, the third holds 18. As you add electrons to an atom, they cannot all pile into the lowest energy state. They are forced into higher energy levels with larger spatial extent. Without the exclusion principle, every electron in every atom would collapse into the ground state, and all atoms would be the same tiny size. Chemistry would not exist. You would not exist. And you can see this in the actual measurements. Hydrogen has a radius of about 0.53 angstroms. Helium is actually smaller, about 0.31 angstroms, because its 2 electrons experience a higher effective nuclear charge pulling them in. But then lithium, with its third electron forced into the second shell, jumps to 1.67 angstroms, and cesium, with 55 electrons stacked into higher and higher shells, reaches 2.98 angstroms. Atoms get bigger as electrons are pushed outward by the exclusion principle, each one forbidden from occupying a state that is already taken. Think about that. The size and shape of every atom in the periodic table, the foundation of all chemistry, all biology, all of you, is determined by the single quantum rule. No two electrons in the same state. That is it. And from that, everything follows. Now, let me tell you about one more way to see why the atom is stable, because I think it is the most beautiful perspective of all. In the path integral formulation of quantum mechanics, the electron does not take one path. It takes every possible path simultaneously. Each path contributes a probability amplitude, a little arrow with a length and a direction. For most paths, the arrows point in random directions and cancel each other out through destructive interference. But for certain configurations, the arrows line up. They add constructively. And the ground state of hydrogen is precisely the configuration where the sum over all possible paths produces a stationary, stable probability distribution. The atom is stable not because the electron is frozen in place, not because something is holding it there. It is stable because when you add up every possible thing the electron could do, every possible path it could take, the result is a fixed, unchanging probability cloud. It is a quantum fixed point. The path integral converges. The electron, in a sense, is doing everything at once, and the net result is perfect stability. Now, you might wonder why classical physics gets this so wrong. And the answer comes down to one thing: scale. Classical physics works perfectly well when the de Broglie wavelength of an object is much, much smaller than the relevant distances. For a baseball flying through the air, the wavelength is about 10 to the minus 34 meters. That is so small that the wave nature is completely irrelevant. The baseball is a particle for all practical purposes, and Newton's laws work beautifully. But for an electron in hydrogen, the de Broglie wavelength is about 3.3 angstroms. That is comparable to the size of the atom itself. At this scale, the wave nature does not just matter, it dominates completely. The electron cannot be treated as a little ball with a definite orbit. It is a wave. And waves do not spiral into point sources. They form standing patterns. You see, the de Broglie wavelength is like a dividing line. Above it, the world looks classical. Below it, reality is quantum. And atoms live entirely below that line. Classical physics never had a chance. So now let me bring this all together because I want you to see the full picture. If the universe ran on classical physics, no atom would survive longer than 16 picoseconds. No molecules would form, no chemistry, no stars, no planets, no water, no proteins, no DNA, no life, nothing. The universe would be a soup of nuclei and radiation, and that would be it, forever. But the universe does not run on classical physics. It runs on quantum mechanics. And quantum mechanics says three things. First, the electron is a wave, not a particle, and waves form stable standing patterns rather than spiraling inward. Second, the uncertainty principle sets a minimum energy and a minimum size for the atom, the ground state below which nothing can fall. And third, the Pauli exclusion principle prevents all electrons from piling into that ground state, giving atoms their structure, their variety, their chemistry. Every time you pick up a glass of water, you are holding something like 10 to the 25th atoms. Every single one of those atoms, classical physics says, should have disintegrated 13.8 billion years ago, within the first trillionth of a second after they formed. They didn't. They survived the entire age of the universe, and they survived because reality is fundamentally quantum mechanical. You know, I think there is something deeply wonderful about this: the stability of matter, the fact that you can sit in a chair and the chair holds you up, the fact that the ground beneath you does not evaporate, the fact that your own body holds together from one second to the next. All of that depends on quantum mechanics. Not in some abstract theoretical sense, in the most concrete, physical, immediate sense possible. Your atoms exist because electrons are waves. Your body has a shape because of the exclusion principle. The ground beneath you is solid because the uncertainty principle will not let atoms collapse. And here we are, made of these atoms, these quantum mechanical objects that classical physics said could not exist, trying to understand how it all works. Our imagination is stretched to the utmost, not to imagine things which are not really there, but just to comprehend those things which are. Remember that 16 picoseconds? That was the prediction. That was how long matter was supposed to last. 16 trillionths of a second and then nothing. Every equation said so. And for 14 years, the greatest minds in physics could not explain why it was wrong. The answer, when it came, was not a small fix. It was not a patch. It was a complete revolution in how we understand reality. Electrons are not tiny balls. They are probability waves. Atoms do not work like little solar systems. They work like standing vibrations. And the stability of everything around you, everything you have ever touched or seen or loved, comes from the wave nature of matter, the uncertainty principle, and the exclusion principle working together. That is not some theoretical idea. This happens. This is happening right now in every atom of your body, in every atom of the air you breathe, in every atom of every star in every galaxy. And that, I think, is beautiful. That is how it works. That is science.